Our next speaker is Dr. Yantian Zha. Yeah. He's giving us a talk regarding perceiving, acting, and planning and self-explaining for future manufacturing. So let's welcome him.
Thank you very much for the great introduction. So, dear colleagues, friends, and students, it's my honor today to give this talk, Perceiving, Acting, Planning, and Self-Explaining, a cognitive quartet for future manufacturing. So imagine when you watch a quartet. So what you just saw is that you will see there are four players who closely collaborated together to play the beautiful song, right? So similarly, in this talk, I will talk about how the different levels of cognitive functions like perception, action, planning, and self-explanation can also closely work together to contribute to a very powerful cognitive intelligence. So let's start from perception action company. And then I will introduce this work published in IROS 2022 called Affordance Aware Imitation Learning. And then perception planning company. And I have done such works like evaluation from learning from observed action distributions and plan recognition during attention. But unfortunately, today we don't have enough time to go through such works. And then I will talk about a higher level cognitive function called self-explanation guided learning, which can guide the learning of the lower level cognitive functions like perception, action, and planning. So far, this is the work that I will talk about today, which was published recently in AAAI 2024, self-explanation guided reinforced learning from demonstrations. So far, I will talk about my research that addresses fundamental robotic challenges, but some of my other research also address human-robot collaboration challenges. So those are my works, and today I will talk about the NetSGD, which is a multimodality dataset that has speech, gestures, and demonstrations. So now let me introduce the first part, perception action company. So I will talk about this work published in IROS. So here's a demo video that I made in 2015 in Real Robot. So pay attention to here, you will see there are some green arrows that are generated on the surface of an object. Those green arrows basically represent the affordance, basically how robots could grasp the object and lift it up. And then this tells robot what should be a target pose so that it can sample a motion plan, and then robot can run the motion plan in the real world. So in the literature, I mean, people have found that if we use supervised learning way to learn affordance, we typically need to label affordance even at pixel level, which is very expensive. So one of the popular research cluster is about learning affordance from demonstrations. And clearly such works would have the benefits of avoiding the needs of doing expensive affordance labeling. However, their limitation is that they assume there is an external motion planner, which can take some carefully designed or engineered affordance features so that the motion planner can directly take them to generate the motion plan. So if we predict such a complex affordance knowledge, it will still be very complex to learn a model to do this. So to mitigate this issue, we got some insights from cognitive psychology. So those cognitive psychologists have found that there is a close association between affordance and attention, meaning that if you focus on an area, for example, a part of an object, you basically is very likely to interact with object on that part also in the future. So in our work, we want to merge learning of affordance skills and policy learning. So you may have a question, what is affordance skill? So short answer, affordance skill is actually essentially visual attention, but this is a special kind of visual attention. This visual attention can give you some hints for you to interact with the object. This is an example of affordance skill. So for example, here is a mark, and you focus on, you are highlighting the handle part. This gives you a hint that you would also grasp the handle, lift it up by grasping the handle part. However, if you look at a different mark, the handle is not easy to grasp because it's too small or too narrow. So you probably focus on the body part. It gives a hint that you would also lift the mark up by grasping the body of the mark. So we found that predicting affordance skills or essentially attention maps tends to be a more efficient way because attention maps are easier to predict. And we can then propose an end-to-end imitation learning framework to take the guidance of affordance skill and then generate a control command. So here is the depth image, and our model predicts affordance skill and another image and another affordance skill and another image, affordance skill, and so on. So what you just saw here are two demonstration trajectories that can grasp two different marks into different ways. So now the question is, what could be a strategy for you to find those affordance skills? For example, the handles for the mark at the top, and the body part of another mark, smaller mark at the body. So the strategy could be that you can ask yourself, what could distinguish the two demonstration trajectories? Then you can see that you can find that the difference will be that for the alpha mark, the handles are larger and easier to grasp, but for the mark at the bottom, it's smaller, but the size of the body is just good to be grasped. So this inspired us to design our framework based on combining contrastive learning and imitation learning. However, if you directly apply the traditional contrastive learning for learning from those demonstration trajectories, I mean the whole trajectory, we found that it cannot just directly work. The reason is that the whole trajectory contains lots of noisy information, but we know that from the definition of affordance, it's about the interaction between the actor or gripper and the object. So the whole trajectory will contain noisy factors like initial states, obstacles, and so on. So to go over this challenge, we propose to extract the segment where the gripper interacts with the object, and we learn an affordance embedding. And from the other side, we want to learn the encoder for encoding observation at any step. So we go from two sides, and we predict the upper ZA is affordance embedding, and the lower ZTOA is observation embedding. And we want to use the affordance embedding to guide the learning of observation embedding. And then we can predict the affordance Q for a policy network. So we propose a corporate trip loss to do this. And I'm not showing the policy network here, but I want to highlight that the policy network is learned simultaneously with the affordance learning. So we evaluated our model in this Panda environment. Here's a demo video. So there are two different marks, and you can see that the humans choose the best way to interact with different marks. And the affordance Q indeed is influencing the behavior of the robot. And what is more interesting is the demo video on the right side. You can see that it follows the findings from cultural psychology. The robot shifts its attention from the handle to the body, and then it decides to pick up the mark by the handle. And here's a grasping success rate. And our model with all the techniques like contrast learning and coupler trip loss performs the best, better than evaluation studies and a baseline state-of-art behavior cloning model. So future directions, our work has some limitations. So one limitation is that our affordance-aware imitation learning makes the perception more conscious, but it still cannot utilize domain knowledge. But our work also opens many opportunities for future research avenues. For example, we can consider what if there are multiple levels of interactions, which is quite common for any tool using tasks. Secondly, we could consider conditioning affordance skill on different high-level task contexts, and then connect to large language models. And thirdly, we can consider if we can use our coupler trip loss to solve other learning problems. Now I'm going to the second part, self-explanation guided robot learning. I will introduce this work, learning from ambiguous demonstrations with self-explanation guided reinforced learning. So when robot learns tasks, one of the core questions is how can we convey task knowledge? Basically, there are two ways. One is we can collect demonstration trajectories to teach robots what's the task to do. Second is we can engineer some reward functions to train the robot. And what could be the third way? I didn't say here, but the third way is to combine both. So actually, there is a quite popular trend in reinforced learning called reinforced learning from demonstrations. So RFD basically combines the benefits of the reinforced learning and the imitation learning, which could make the reinforced learning more sampling efficient. However, we do find that even state-of-art RFD has some limitations. For example, it still cannot handle challenging environments where there are some kind of high degrees of ambiguity. So this could be a bottleneck. And to solve this issue, we also got some insights from humans' cognition. So for example, when humans learn complex knowledge, we tend to be aware and reflective of our own learning. So which means that we could explain our past experiences, we talk to ourselves in our mind, and through this procedure of doing internal monologue, we could obtain some insights which can guide our future learning and make our learning more efficient. However, for robots to learn from humans, we assume that it makes sense for robots to understand humans' teaching with some kind of humans' background knowledge. For example, if for you to understand my talk, you probably need to understand English, right? It's the same thing for robots to learn from humans. We assume robots would understand the environment through the lens of some shared vocabularies with humans, so that the robot can detect which of those relations are there in the current observation. However, what is interesting here is that there is an ambiguity in the environment and the task, which means that not all of those satisfied relations are important or relevant to the task. So that's why robot will need to do self-explanation. And when robot conducts self-explanation, it basically would select one or multiple predicates or relations and assume that they are important to a task. So those are in the U column. It's like the symbolic attention. So for this step, and in this case, the robot is assuming that the predict green and blue is important to solving the task. So now for the self-explanation reinforced learning from demonstration framework, when robots learn to take humans' advice, we have a reinforced learning model as robot, and we learn from humans' demonstrations. And we assume demonstrations could be ambiguous because the environment is very challenging. So the reinforced learning can also drive the robot to interact with the environment. So pretty obviously, we could have successful samples and failure samples, and then the robot would self-explain by distinguishing between successful and unsuccessful experiences and explain why a successful experience is successful. So basically, it can detect some insights or distinguishable features from the self-explanation. And when robot conduct self-explanation, robot also needs to refer to the human-related background knowledge. And then use a self-explanation to guide the reinforced learning from demonstrations, either through augmenting the state space or shaping the reward or doing both. So we evaluated our SRFD in 4 domains with different degrees of ambiguities. So to get an intuitive sense of ambiguity, we can say there are different predicates in the environment, and so there are different degrees of ambiguities. And here I'm showing a demo video, which is predicted self-explanations from our model. So you can see that there is a P column, meaning how many predicates can be detected in any step of observation. And the U column is a self-explanation. And you can see that there could have multiple predicates to be detected, but not all of them are important to explain why the demonstration is successful. So robot assumes that cylinder push to yellow region is more relevant to the success of a task, and the robot indeed follows this self-explanation and push the cylinder to the yellow region. And this environment actually is more challenging than what I explained. Assume that if the cylinder object was initially located on the left side of the table, robot needs to remove this black cover and push to the target region. But if the object was initialized on the right side of the table, then there is no need to remove the black cover. So you can see on the demo on the left side, the robot figured out a very smart way to accomplish this task. And here is our reinforced learning training results. So for the red curves, aqua curves are those models that used our self-explanation. You can see for the more challenging domains, the models with using our self-explanations tends to have a much better performance and can be trained more stable. So future directions. One limitation is that our background knowledge is predefined and is a finite set of predicates. And for future opportunities, first is people could consider improving the self-explanation guided learning. For example, can we use large language models to solve the limitation? The second possible future opportunity is we could use self-explanation guided learning to improve many other learning frameworks. Reinforced learning from demonstration is just one example that we have considered in our paper, but there are many other learning paradigms. The third point is that we could use the power of self-explanation guided learning to solve a diverse set of problems and challenges. Now, I want to introduce you the human-robot collaboration part. So this is work that I have doing with Yannis here, sitting here, and with the PRG group. So it's a multimodality data set that has speech, gestures, and demonstrations. So to better explain the motivation, let me give you this example. So in this case, the lady said that pass me that plate is pretty like a natural way that you probably would say to your friend, your kid. You will not say that please pass me the plate in red color on the rightmost part and so on. You will say briefly, pass me that plate, please, and also point to a plate. So it means that for human to humans natural communication, we tend to use both speech and gestures. But the current works, if we only use speech, it will be impossible to get the meaning correctly. So there are many benefits of understanding both speech and gestures. One is that if robots can understand both speech and gestures, it allows the humans to naturally interact with robots as if interacting with another human. The second benefit is that robots can obtain additional context information by understanding gestures. The third benefit is that a robot can it can make the communication more efficient because the humans can use both speech and gestures. Lastly, you know, we could have different cultural backgrounds. Sometimes different language and people speaking in one language may be hard to understand another person speaking in another language, but the gestures would be similar. So now here's an overview of our SGD dataset. We have a robot and we have a human. The human user speaks to the robot while also showing gestures. And there's a human expert who would control the robot and react corresponding to the understanding of the speech and gestures. So then we can collect the three parts: speech, gestures, and demonstrations. And then we can use that to train many downstream robot learning tasks. And we had 18 people. Our data set includes 18 people to instruct the robot through speech and gestures. And we have a robot expert to control the robot and react to the humans who give commands to the robot. And here is our data set. Our data set includes speech and gestures, and also different camera viewpoints, and RGB and depth information, and the ground truth instant segmentation and semantic segmentation. And of course, we also have a rich annotation at different levels, like object bounding boxes, activities, events, and so on. Now here is the demo video of our data set. So there's a human standing in the center, talking and showing gestures to the robot. And you can see how robots react to those speech gesture commands. Okay, so now it's time to talk about how can we evaluate our data set through some benchmark tasks. So our task is multimodal task understanding. So we have a human which talks and shows gestures to command the robot. The multimodal task understanding is essentially a translation problem. So the model translates the speech gesture commands to some kind of control commands for the robot. Now the question is, how can we represent the task understanding of the robot? It's actually not an easy question. So to better explain, I need to give you an example. In this example, there are many carrots putting on the sink, and there are a few of other carrots here. So the human commands the robot by saying that cutting those, and while also pointing towards the carrots, right? Now, how can you solve this problem? We could consider a tree structure to show the procedure. So, 1 second. Initially, the carrots are in a sink. Next state could be the carrots are grasped, and then the robot could put the grasped carrot on the cutting board. Now there are two ways to continue. Two possible future states. One is that the carrots on the cutting board are cut into pieces. The second possible next state is that the human could grasp another carrot. Now we can select either of the branch to continue. So we select this, and then there are again multiple possible future states For example, the human can grasp the cutting board or can grasp another carrot. If we go along this direction, then the human can pick up the cardboard and pour the carrot pieces into a bowl. And then the robot can then go back to grasp another carrot, and so on. However, if we expand this along another node, we can go to this like carrot on cutting board, and to opportunity to possible next stage, and so on. We can say this is very complex. The structure is complex. We cannot use this to represent the understanding of humans' comment, cutting this, right? So this inspired us to consider linear temporal logic, which is designed to represent the complex temporal logic in a very compact way. So then our task becomes to translate speech structure comments to LTL formulas. So we annotated those number of LTL formulas for over 1,000 pairs of speech and gestures. There are lots of benefits of doing LTL. For example, we can better use the power of language models. We can connect to other logical reasoning and planning systems. We can also connect the LTL to automata. So then our learning task becomes to learn a mapping from speech and gesture to this LTL representation of a task. And we can also have ground truth LTL formulations. And here's our evaluation. We consider the different baseline language encoding models. And you can see that if we use both speech and gestures, it performs best. Okay, so future directions. One of the limitations is that our dataset is limited to kitchen environment. But our dataset indeed open many opportunities for future works. For example, we can expand the dataset to a wide range of tasks, environments, and languages. We can also integrate human interjection scenarios. For example, when humans was doing some task, sometimes they may need to stop and look back to a robot and understand the robot may need to stop and look back to human to understand gestures and speech. And finally, we can use the dataset to solve different learning challenges. So my research covers perception action company, perception planning company, self-explanation guided robot learning, human-robot interaction learning. So what's next? So with all of those companies of different cognitive functions, we can build around five or six. Yeah. So we can have a better intelligence, and then we can consider building new robots, and we can have new morphologies, kinematics, controllers, functions, and simulators. Now I want to talk about ongoing work about underwater manufacturing. So here is yeah. So this is the area aquatic manipulator in sea area and land simulator. So the contribution has two parts. One is the new robot, which is a robot that can fly into water, grasp, and get out of water. So the robot, here is a robot. So there are 4 rotors that can rotate and make it better swim in the water. And the manipulator can also be changed. And on the other side, we have built the simulator part. That includes land and sea and air. So we have compared different kinds of dynamics, and we can show that they show the same behavior, which can verify our dynamics implementation. And we have implemented different control architectures and environments. I want to show this demo video. Here is a cold water that can swim, go in water and swim and get out of water. And robot can also manipulate. So the limitation is that we need to better estimate the sim to real transfer, but many opportunities, for example, we can use that to help develop physical area aquatic manipulators, which is another ongoing project. And we can introduce dying battery effects and attach a second manipulator to explore new opportunities. So now I want to thank you to my faculty collaborators, especially my advisor Yanis, who is sitting there. And I'm also fortunate to collaborate with your students. And finally, I want to thank you to my students who are sitting at different locations. Okay, thank you for the talk. Thank you for listening to my talk. Now I'm happy to take any questions.